Hey YouTube, it's Steve at Op Engineer. Thanks for joining me and welcome back. I've got a new video on electrical safety. So, I'm going to be talking a little bit about the NEC, NFPA 70E, and then got my old copy of NESC, IEEE, National Electric Safety Code. I think it's a good transition from my last video on engineering, how to be a profession, because safety is a foundational element of every profession. When a government decides to create a licensure and allow electricians to work or professional engineers to work, a lot of times it's in the interest of the public good or the individual performing the work to make sure that things are done right and nobody's going to get injured or lose property. So let's get started. Again, just a reminder, this is all my own personal opinion. It's not the views of anybody else or any of the organizations I mentioned in here. And if you have any questions, please feel free to comment in the boxes below. Keep it family friendly. And if you would like to subscribe and like, go ahead. Thanks. Alright, so what is electrical safety? Thinking about beekeepers aren't going to go out to their hive with shorts and a t-shirt on and start working. They're going to be taking proper precautions by wearing protection and knowing how to work around bees so they don't get stung. So I'm not talking about the malicious behavior and bad decisions with protection and security. Security protection could play a role in the amount of energy, but that's a whole topic in and of itself. I'm really focused on electrical safety being the performance-based around construction, operation, and maintenance for equipment and personnel. So when we're talking about electrical safety, that is being able to identify hazards associated with electrical environments and then being able to take action to eliminate and mitigate those hazards when performing construction, maintenance, operating, or just generally living around those areas. So making sure people are properly trained and aware of those. The NFPA 70E defines electrical safety as identifying hazards associated with the use of electrical energy and taking precautions to reduce risk associated with those hazards. Here's some electrical safety stats. Most of it's from the BLS, Bureau of Labor and Statistics. Oops, let me back up there. In summary, here you can see there was a big improvement between 2003 to 2009 timeframe to 2011-2015, where electrical injuries resulted in fatalities much more frequently in the early 2000s than they did 2011-2015 timeframe. So improving by like a factor of 10, but still not much more of a threat than like fall injuries, for instance. Conclusion is people who are working around electrical hazards and fall hazards, for that matter, are going to be more susceptible, obviously. So making sure that those individuals are properly trained and working around the correct equipment is going to be important to their safety and the safety of everybody in the area. So a little bit of history on electrical safety. Electricity and electrical technologies really got kicked off in the 1800s with the patents of the telephone, the phonograph, and then the construction of new generation facilities in the 1876 to 1887 time frame, where technologies that were patented, such as the telephone, phonograph, and then eventually the light bulb, created a huge market demand for electrical components, which drove the drove people to build facilities, power plants, and then eventually form organizations to supply that market. Right? And as that was happening in the 1800s, eventually, with all this new technology and electricity being a safety hazard and the safety hazards that are associated with electricity. People were getting injured more frequently, and you realize that little Billy, without any training, straight out of middle school, can't do the same work as somebody who's been working around electricity for a while and understands the hazards involved. So people started getting organized towards the end of the 1800s by creating the Joint Conference for Electrical and Allied Interests, and then eventually the formation of a National Electric Code in 1897. Around the same time, a lot of research was being done to better understand electricity as well as the hazards involved with it. In the early 1900s is when a lot of the organizations started getting backing from government to make it federal code and giving the government some sort of authority to enforce those standards so that workers were safe, workers and the general public were safe, and that they were getting their money's worth for the new technologies that were being put out there. So in the early 1900s, really the World War II time frame to the 1950s, there was a rise in interest to understand how electricity affected the body, and I think it was Anna Stoll developed the relationship between pain and tissue damage due to electrical, but her focus was on aerospace and thermal radiation, but the application to the electrical industry was huge because of that. And eventually the formation of the occupational OSHA, Safety and Health Act in 1970 gave the federal government grounds to enforce labor standards to a certain degree. And then in the 1970s, they developed Dalziel, I'm not sure how you pronounce that name exactly, but did the theoretical research for understanding shock hazards, which was eventually built upon by Drought and Nadeau, understanding arc flash. So we'll get into the specific electrical hazards in just a minute, but and you'll see where that and the Lee's equations on his research for electrical arc blast and burns came into play. And then NFPA 70E in 2000 came up with risk categories on electrical protection. So you can see kind of the evolution from big market and increased hazard environment drove the need to understand how the hazard was interacting with personnel and their job functions or their living conditions. And then once that theory was developed, they were able to enforce it with code in the form of the code and standards in the form of things like the NFPA 70, and we'll get into more of that later. So, electrical hazards. Talking about electrical hazards, they generally can be thought of in terms of these four components. So electrical hazards can be in the form of electrical shocks, which is current passing through the body. Ouch. Resistive burns, which could be current passing through the body and heating it up, but it could also be like a stovetop induction coil, where that's electricity running through that coil that creates resistive thermal output that we can use for a lot of things, but it can also be a safety hazard. So look out for that. And then you got electrical arcs, which like a lightning bolt or electrical arc blast, as you might hear them called. Electrical arcs can produce huge thermal output and pressure waves that damage people, personnel, property, and you want to look out for that one. And then there's material corrosion or degradation. Honestly, a lot of standards and codes don't refer to this in electrical environment a whole lot, but it is a thing. Everybody's seen corrosion on their batteries in their cars, probably. So you can imagine there's things that go into like bimetallic strips, making that allow you to prevent corrosion from mechanically degrading the structure of transmission line connectors or cabinets and so forth. So corrosion is a thing too, but not talked about nearly as much as shocks, burns, and arc flash. So yeah, that's a typo there. So shocks and burns. Electrical current passed through the body as a result of energized equipment. So this could be something as simple as a wall outlet or loose conductors that you can grab onto and receive a shock through your hand. That's current passing from one electrode to the other and damaging your tissue or just producing pain, as you can probably imagine. Or it could be something like electrified equipment, like an electrical cabinet that's got a loose conductor hanging against it, or something like a down conductor that's causing a piece of steel to be energized, and you go up and touch it. The current would then pass through your body to the ground and back to the energy source. That's referred to as touch potential. So the energy path is going through your arm and down through your leg into the ground or wherever it's coming out. Or it could be just a step potential. If there's a, say, downed conductor or a short from a high voltage line to ground that releases a lot of power, all that voltage in the line is getting dumped into the ground, and you can imagine it like water seeping through the dirt. It's not all going to seep instantaneously into the ground, so you get a buildup of voltage in that area. The voltage will have a gradient back to the ground source, and whatever that gradient is, that's a potential, that's your step potential. So any of that is going to be creating current that could potentially flow through your body, through up one leg and out the other leg. Not fun. So yeah, as I mentioned earlier, the Stoll curve or Stoll equation came up with a good theory on what current passing through a person what effect it has. So you have a slight sensation around 1 milliamp. Up 10 from there, you really you can obviously perceive it and start to feel a shock. At 100 milliamps, you start to have heart problems if the current passing directly through that part of your body. So and then burns just at just 2.5 amps. So 0.1 amps basically is enough to create life-threatening injury to a person. So electrical shock and burn hazard is an issue there. All right, arc flash. So arc flash, it's a little bit more of a complicated topic, but you can pause it here and read through this. Generally, you have two electrodes, and the dielectric between those two electrodes break down, such as air. You see it in welders or lightning, for instance. That plasma that's formed between those two electrodes can get up to 35,000 degrees Fahrenheit, which is hotter than the surface of the sun by quite a bit. And it's going to release a lot of heat, and depending on the amount of power, it could release a pressure wave, and as well as molten or solid pieces of debris, gaseous fumes that are toxic, and yeah, bad deal. So arc flash, consider two conductors. How does it happen exactly? Two conductors. You have your say here your negative conductor in blue, positive in red. So there's going to be a potential difference between those two conductors. You could also have a potential difference between the line to ground. So ground being neutral, there's a voltage there. So when I say potential difference, I mean voltage. So you have a line-to-line voltage, you have a line-to-ground voltage. Those could both potentially be sources of electrical arc flash hazard. As the electric field or the voltage grows, as the voltage grows between two conductors, you have an invisible electric field that's growing with that between those two electrodes. And when that gets to a certain point, your electric field starts to conduct from one electrode to the other. And you won't be able to see it at first, but it's going to be going through a phase called dark discharge, where those electrons start to leap off and run into other electrons. Once it gets to a certain point, you have a breakdown or electron avalanche, where the electrons are jumping off with such a velocity, running into other electrons, that you start to have these plasma jets or plasma leaders form in the form of a glow discharge. So the air is starting to ionize. That means that they've got extra charge that is passing through between the two conductors. And eventually that electrical leader that's avalanching down will come in contact with the other conductor, or get to a point where the plasma trail connects the two, and plasma is just a flow of resistance-free, basic or very low resistance conductor from cathode to anode. You get basically a short circuit, and once you got that short circuit, the voltage is going to collapse and the current is going to begin to flow freely. So to illustrate that, you get one electron run into more, avalanche effect happens. You start to have leaders forming. Those leaders form until they complete the circuit in a plasma trail, and boom, you get an arc flash event. So the current goes up to whatever is limiting it in terms of power. The energy source is going to dump all of its energy at that point. So again, if you think about it as water, if you've ever heard the analogy as the amount of water flowing through a stream is kind of like the amount of electrons flowing through a conductor. So you can walk into a stream knee-high, not going to really have an effect unless that stream has a drop, like falls or something that causes the water to move fast, and you can start to have the water sweep your feet out from underneath you. And so you get to the point where you can't control the force of water. Same thing with electricity. Once the electrons gets too high, the current gets too high, that's where you run into issues. So hopefully that helps explain what is electrical arc flash. All right, so qualified electrical workers tend to be anybody who's been trained, tested, and completed a mentorship by somebody else who's considered competent in their field, or in some cases, as an electrician or a PE, legally qualified to perform work in a certain field or around certain equipment. They will test you out, and key thing to note here is not all operators, maintainers, or construction workers are considered equal, right? So if you're qualified to operate a piece of equipment, you might not be qualified to maintain it or to construct it. So this is important. This is a key word, qualified electrical workers, that goes into electrical training. And being able to recognize those electrical hazards. Another key word here is electrically safe working conditions. So again, following the principles of electrical safety, creating a safe work environment means that any energy hazard source or hazardous energy sources are disconnected, de-energized, locked out, and or tagged out if needed, and tested to prove that it's in a grounded state, and that it's in accordance with local code and accepted standards. So, key word there is electrically safe work conditions. Electrical safety and code and standards comes in many flavors depending on what you're working on, but generally this is a list of key stakeholders. You got your federal enforcement, so OSHA, which is created under the U.S. Title 29 Code of Federal Regulation, Part 1910. And then there's also the Code of Federal Regulation 1926, which is not OSHA, but for electrical worker safety. And then there's the National Fire Protection Agency, who produces the 70E or the NEC, which many people are probably familiar with. That's the code for a lot of residential type construction. Generally, it's 600 volts and under, depending on your situation. And then there's the National Electric Safety Code, the NESC, produced by IEEE for generally voltages over 600 volts. So utility, electrical supplies, refineries, chemical processing plants, things like that. Word of note for those, the NFPA 70E, 70, NESC, these are not like design guides. They're not going to teach you how to build a house or wire a house, or it's a set of code that, given whatever your conditions are for your circumstances for maybe building a house or set of electrical inputs, you can define like, are you installing a motor in an environment that has hazardous gases around, or are you working with emergency fire equipment? It's going to take whatever electrical characteristics inputs you have and then tell you what the minimum equipment is to install it safely. Or in the case of 70E, what type of safety equipment and training you need to do it safety. And then you got your other organizations like NEDA, which further qualifies people to perform work around electrical equipment. NEMA, which they define how to build, manufacturing things safely. UL, which is the underwriter's laboratory. They do a lot of testing and analysis on electrical equipment to say that your wall wart charger for your phone is not going to burn down if you leave it plugged in for a year on end. And then you got your ASTM electrical testing for materials. IEEE produces a whole bunch of other white papers, conferences, and books, like the buff books that go beyond just safety and into protection and new technology development. And then you got your IEC, International Electrotechnical Commission, I believe it is, which is like the NEC for international. Canada has their own as well, and all these organizations play a role in the overall architecture of electrical systems. So to further clarify that, if you think about your electrical code broken up by installing different equipment, NESC IEEE C2 is for everything on the utility side or refinery or high voltage stuff. So the distribution feeder, step down transformer, disconnect switch, fuses, and really the utility kind of owns everything up to the meter usually, but the code for installing that class of equipment is outlined in the NESC, and then there's some overlap with the NEC on how to install the residential lower voltage manufacturing industrial equipment, NES or NEC, National Electric Code, which is again written by the National Fire Protection Agency. Their standard 70. And then encompassing all of these are the groups that qualify the workers, equipment, and materials being used. So again, NETA, they have outlined for different types of working conditions. I'll get to that in a little bit. And NEMA for manufacturing equipment, say you want a watertight enclosure or an enclosure for equipment that's used in a hazardous environment. Make sure you look at the NEMA standards to see what's qualified for to be safe in hazardous environments, to make sure like corrosion of a box doesn't affect electrical safety of whatever is inside that box. UL listing to come up with standards for equipment manufacturing and use, really, and yeah, so forth. So you got those organizations which kind of encompass the installation code, NESC and NEC. So drill a little bit deeper. OSHA, which is the federal authority having jurisdiction over labor standards. They outline in 29 CFR 1910 the OSHA standards. Subpart S is electrical. They define their relationship with the NEC in 1910-.3, I believe, and then the standards for electrical installation is that 301 to 399 section. The Code of Federal Regulation 1926 is for electrical construction safety and health regulations, and it's broken up by electrical workers or electrical transmission distribution workers, respectively. So, electrical safety organizations also include, I mentioned earlier, the NFPA 70E, 70, NEC, and the NFPA 70B. So NFPA 70E, that's for workplace standards on electrical safety, personal protection equipment, training requirements, calculations for arc flash hazards, for instance, and the NEC is the code for installing equipment. So given a certain requirement to install based on a design, the NFPA 70 NEC, the National Electric Code, is not a design guide. You will refer to your design guide to reference the NEC and determine how something is supposed to be installed. NFPA 70B is recommended maintenance requirements. And then the IEEE NESC is not nearly as detailed as the NEC. If you think about it, just in terms of number of people, there's a lot more residential work going on, and it's standardized in a way that it doesn't change from place to place nearly as much as issues you're going to see in the NESC. So by that, like for instance, building a substation on the East Coast next to the ocean in an area with a ton of lightning is going to be a little bit different than building a substation in the middle of the desert, up on top of a mountain, right outside of a dusty coal mining processing facility, and so forth. So NCES is going to kind of help with those broader scale geographic higher voltage problems in a less detailed way. Generally, the workers are more highly trained that are using the NESC, or they are working on more unique equipment that is like a custom install, because it's I don't want to say custom, but it's that utilities standard. So, and then NETA, National Electric Training Association, or excuse me, International Electrical Testing Association. They create standards for testing technicians, testing equipment, maintaining equipment, accepting new equipment, and then commissioning specifications for installing new equipment. Right. So that's all I got for electrical safety overview. Again, this is like the 10,100 mile view of electrical safety. It's not meant to be a deep dive. And again, these are all my opinion, just provide references and an overview of electrical safety. Hope you enjoyed the video and have a good day.